Hello there and welcome. Tonight's gentle journey takes us to the most mysterious objects in the universe, black holes. These cosmic giants swallow light itself, bend space-time like cosmic trampolines, and hide secrets behind veils we may never lift. But before we drift toward these gravitational monsters, I'd love to know where in the world you're watching from tonight. And can you see any stars through your window? Fitting, isn't it? Here we are, safe in our beds, contemplating the universe's most dangerous neighborhoods from the comfort of blankets and pillows. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something about the universe's most extreme phenomena before you drift off. So settle in, slow your thoughts, and let's begin our descent into the cosmic abyss. Black holes have always captured human imagination in the most peculiar way. They're invisible by definition, yet they've become the most famous objects in astronomy. They represent everything that's both terrifying and beautiful about the universe: ultimate power, absolute mystery, and the complete breakdown of everything we think we understand about reality. Children draw them as swirling spirals, science fiction writers use them as cosmic doorways, and physicists lose sleep trying to understand what they really are. They're like cosmic riddles wrapped in mathematical enigmas, tucked inside regions of space-time that have decided to play by completely different rules. The very name black hole was coined relatively recently, in 1967 by physicist John Wheeler, though the concept had been lurking in the shadows of physics for much longer. Before that, these objects were called frozen stars or dark stars, names that somehow felt less ominous than the cosmic vacuum cleaners we know today. There's something almost playful about Wheeler's naming choice, as if he were describing a particularly deep puddle rather than a region where the laws of physics go to retire. But perhaps that gentle naming helps us sleep better at night, knowing that even the universe's most extreme phenomena can have friendly, approachable names. What makes black holes so uniquely unsettling isn't just their incredible power, but their fundamental hiddenness. Every other object in the universe reveals something about itself through light. Stars shine, planets reflect, gas clouds glow with their own gentle radiance. But black holes are cosmic secrets, regions where light goes to disappear forever. They're like astronomical magicians who've pulled the ultimate vanishing act, except the audience never gets to see behind the curtain. We can only infer their presence by watching how they affect everything around them, like detecting an invisible dancer by observing their partner's movements. The mathematics that describes black holes reads like poetry written in equations, full of infinities and singularities, event horizons and space-time curvatures that would make geometry weep. These aren't just academic abstractions. They represent real places in our universe where matter becomes so dense that it creates permanent wrinkles in the fabric of reality itself. It's as if the universe occasionally decides to create regions where the normal rules simply don't apply, cosmic special economic zones where physics operates under different legislation entirely. And yet, despite their reputation as cosmic monsters, black holes are surprisingly common. Our own galaxy likely contains hundreds of millions of them, quietly going about their business of warping space-time and occasionally snacking on nearby matter. Most of them are stellar mass black holes, the remnants of massive stars that decided to exit the cosmic stage with the most dramatic finale possible. Others are supermassive behemoths lurking at the centers of galaxies, including our own, where a black hole weighing 4 million times more than our sun sits patiently at the Milky Way's heart, like a cosmic cat napping in a sunbeam. Tonight we'll explore what might happen if you were to fall into one of these gravitational giants, though I should mention that this is purely theoretical. The universe has thoughtfully placed the nearest black hole far enough away that you're in no immediate danger of accidentally stumbling into one on your way to make tea. The closest known black hole is about 1,000 light years away, which means even if you could travel at the speed of light, it would take you a millennium to reach it. That's longer than recorded human history, so you can rest easy knowing that black holes, for all their cosmic drama, are safely distant from your evening routine. But in our imagination, we can venture safely to these impossible places, explore regions where time slows to a crawl, and space itself becomes twisted beyond recognition. We can fall past event horizons and contemplate singularities from the comfort of our beds, marveling at how the universe has managed to create objects so strange that they seem more like mathematical fantasies than physical realities. Because that's the beautiful thing about astronomy. It lets us be cosmic tourists, visiting the most extreme destinations in the universe without ever leaving home. A black hole isn't actually a hole at all, despite its rather misleading name that has confused generations of curious minds. It's more like an incredibly dense object, so massive that its gravity prevents anything, even light itself, from escaping once it gets too close. Imagine trying to throw a ball so hard it never comes back down to Earth. But instead of needing to throw impossibly fast, gravity has become impossibly strong. That's the cosmic sleight of hand at work here, where the normal rules of throwing and catching have been replaced by something far more dramatic and permanent. The boundary around a black hole, the point of no return, is called the event horizon. It's not a physical surface you could touch, like the shell of an egg or the surface of a lake. Instead, it's more like an invisible line drawn in space-time itself, beyond which even photons, those massless particles of light that travel faster than anything else in the universe, simply surrender to the overwhelming gravitational pull. Think of it as a cosmic customs checkpoint, where everything is allowed to enter but nothing is ever permitted to leave, no matter how compelling their reasons or how much they might miss home. To understand just how profound this is, consider that light is the ultimate escape artist of the universe. Light routinely escapes from the cores of stars, traveling through thousands of miles of dense plasma to reach the surface and then journeying across millions or billions of miles of space to reach our eyes. Light bounces off mirrors, refracts through prisms, and somehow always finds a way to illuminate even the darkest corners of the cosmos. But at a black hole's event horizon, even light meets its match. It's as if the universe has finally created a gravity so strong that even its fastest messenger service has to admit defeat. The formation of this gravitational prison begins with matter, ordinary matter, like the stuff you're made of, but compressed beyond anything we can easily imagine. We're used to matter having boundaries, structure, the comfortable spaces between atoms that allow electrons to orbit their nuclei in neat, predictable patterns. But in the heart of a collapsing massive star, the pressure becomes so intense that these normal atomic arrangements simply collapse. Electrons are forced into protons, creating neutrons, and then even neutrons are compressed beyond their normal limits. It's matter having an existential crisis, forced to abandon everything it thought it knew about how to behave. What emerges from this cosmic compression is something that challenges our basic understanding of what objects can be. A black hole's mass might be dozens of times greater than our sun, but all of that mass is theoretically compressed into a single point called a singularity. Its density taken to its mathematical extreme, where the normal concept of how much space does this take up becomes meaningless. If you could somehow compress the entire Earth down to the size of a marble, while keeping all its mass, you'd have created something with density approaching that of a black hole's interior. Your marble-sized Earth would contain every mountain, every ocean, every pizza you've ever eaten, all squeezed into a sphere you could hold in your palm. But the truly strange thing about black holes is that they're not solid objects in any sense we'd recognize. There's no surface to land on, no boundary to touch. The event horizon is simply the distance from the center where the escape velocity equals the speed of light. Inside that radius, space itself becomes so warped that all paths lead inward. It's like being inside a cosmic funnel where the walls are made of space-time itself. And no matter which direction you try to go, you inevitably spiral toward the center. Even light, which normally travels in perfectly straight lines through flat space-time, finds those lines curved inexorably inward. The mathematics that describe black holes reveal something even more unsettling. They're not just objects in space, they're distortions of space itself. Einstein's general relativity tells us that massive objects curve space-time, and black holes represent the extreme case where that curvature becomes so severe that it closes off a region of the universe entirely. It's as if space has developed a cosmic hernia, a place where the normal geometry breaks down and creates a pocket that's somehow separate from the rest of reality. This geometric interpretation helps explain why black holes are so absolute in their grip. It's not that they have particularly strong gravitational fields, in the sense of a force reaching out to grab things. Instead, they've so thoroughly warped the local geometry of space-time that falling in becomes less like being pulled by a force and more like following the natural curvature of space itself. Objects near black holes don't so much get sucked in as they simply follow the new rules of geometry in that region, rules that happen to point exclusively toward the center. Perhaps most remarkably, the size of a black hole's event horizon depends entirely on its mass. Double the mass, and you double the radius of the event horizon. This creates a curious situation where supermassive black holes, despite being millions of times more massive than stellar mass ones, are actually much less dense overall. A supermassive black hole might have an average density less than water, while a stellar mass black hole packs enormous mass into a tiny space. It's like the universe has decided that the bigger the gravitational prison, the more spacious the cells can be. The event horizon also has another peculiar property. It's a one-way membrane in space-time. Information, matter, energy, even theoretical messages in bottles can cross from outside to inside, but nothing can ever make the return journey. This creates what physicists call a causal disconnect between the interior and exterior of the black hole. What happens inside can never influence what happens outside, making the interior of a black hole perhaps the most private place in the universe. It's cosmic confidentiality taken to its absolute extreme, where secrets remain secret not by choice or encryption, but by the fundamental geometry of space-time itself. Most black holes begin their lives as massive stars, typically at least 20 times heavier than our gentle sun that rises each morning to warm your coffee and light your garden. These stellar giants live fast and die young, burning through their nuclear fuel with the cosmic equivalent of a sports car engine running at full throttle. While our sun will shine steadily for about 10 billion years, sipping its hydrogen fuel like a careful tea drinker making a cup last all afternoon, these massive stars consume their nuclear reserves in mere millions of years. It's the astronomical version of living paycheck to paycheck, except the paycheck is fusion energy, and the bankruptcy is a catastrophic gravitational collapse. For most of their lives, these massive stars exist in a delicate balance, like cosmic tightrope walkers performing the universe's longest balancing act. In their cores, nuclear fusion creates tremendous outward pressure, pushing against the star's own gravity, trying to crush everything inward. It's a stellar arm wrestling match that can last millions of years, with fusion and gravity locked in perfect opposition. The star burns hydrogen into helium, then helium into carbon, carbon into oxygen, oxygen into silicon, each step requiring higher temperatures and more extreme conditions. It's like a cosmic kitchen where the chef keeps turning up the heat, cooking increasingly exotic dishes from the periodic table. But eventually, these stellar giants reach a point where even their nuclear creativity runs out. When they try to fuse iron, something remarkable happens. The process actually absorbs energy rather than releasing it. Iron fusion is nature's way of saying, that's quite enough nuclear cooking for one star. Suddenly, the outward pressure from fusion disappears, and gravity wins the arm wrestling match in the most dramatic fashion possible. The core collapse happens so quickly that if you could somehow watch it in slow motion, you'd see the stellar equivalent of a controlled demolition, except there's nothing controlled about it, and the building is the size of a small solar system. The collapse itself is almost impossibly rapid. In less than a second, matter equivalent to our entire sun gets compressed from the size of Earth to something smaller than a city. The core temperature skyrockets to hundreds of billions of degrees, hot enough that if you could somehow place a grain of sand at that temperature anywhere on Earth, it would kill everything within 100 kilometers from radiation alone. The density becomes so extreme that a teaspoon of the material would weigh as much as Mount Everest, if Mount Everest were somehow compressed into something you could stir your tea with. This catastrophic compression triggers one of the universe's most spectacular fireworks displays, a supernova explosion. The collapsing core rebounds, sending a shockwave racing outward through the star at thousands of kilometers per second. When this shockwave reaches the star's surface, it blows the outer layers into space with such violence that the explosion can briefly outshine an entire galaxy containing hundreds of billions of stars. For a few weeks, a single dying star can emit more light than all the other stars in its galaxy combined. It's the universe's way of making sure everyone notices when something truly extraordinary is happening. But while the outer layers of the star are being scattered across interstellar space, destined to become the raw material for future generations of stars and planets, something even more remarkable is happening at the core. The matter there has been compressed beyond any normal state, beyond even the ultra-dense material found in neutron stars. At this point, not even the nuclear forces that hold protons and neutrons together can resist the gravitational collapse. The matter effectively disappears from our normal understanding of physics, compressed into what we call a singularity, a point of theoretically infinite density where the laws of physics as we know them simply give up and go home. The formation process creates some of the most extreme conditions imaginable anywhere in the universe. During the collapse, the gravitational field becomes so intense that it begins to noticeably warp space-time itself. Time starts to behave strangely, running slower and slower as the collapse accelerates. Space itself gets twisted and curved until the normal geometry we're used to breaks down entirely. It's as if the universe is being forced to create a region where the normal rules of reality no longer apply, a cosmic exception to the laws that govern everything else. Interestingly, not all massive stars become black holes. Stars between about 8 and 20 times the mass of our Sun typically end their lives as neutron stars, objects so dense that a sugar cube of their material would weigh as much as a mountain, but not quite dense enough to collapse into black holes. These neutron stars are fascinating objects in their own right, spinning rapidly and emitting beams of radiation like cosmic lighthouses. But they represent the last stand of normal matter against gravity, the final state where atomic structure, though severely compressed, can still maintain some recognizable form. The boundary between neutron star formation and black hole formation is remarkably sharp. Add just a little more mass to a collapsing star, and instead of creating an object where matter is compressed to its absolute limit, but still recognizable as matter, you get something where matter disappears entirely into a singularity. It's like the universe has a very specific weight limit for how much stuff can exist in normal space, and exceeding that limit doesn't just make things a bit more compressed, it fundamentally changes the nature of reality in that region. What emerges from this violent birth is something that seems almost paradoxical, an object with tremendous gravitational influence that's essentially invisible. The newly formed black hole retains all the mass of the original star's core, but now that mass is hidden behind an event horizon, cut off from the rest of the universe in a way that's permanent and absolute. It's like having a massive invisible weight sitting in space, detectable only by how it affects the motion of nearby objects. Astronomers often discover black holes not by seeing them directly, but by watching stars orbit around apparently empty points in space, dancing with invisible partners in a cosmic waltz. The event horizon that forms around the new black hole isn't created gradually. It appears suddenly when the collapsing matter reaches a critical density. One moment you have an extremely dense but still observable object. The next moment you have an event horizon surrounding a singularity. It's one of the few truly instantaneous processes in physics, a boundary that appears as quickly as turning off a light switch. The universe seems to have a very binary approach to black hole formation. Either you're a normal object that can be observed and studied, or you're a black hole that hides forever behind an event horizon. There's no middle ground, no gradual transition, just a sudden shift from observable to permanently hidden. The event horizon is perhaps the loneliest boundary in the universe, a cosmic point of no return that makes every other boundary seem negotiable by comparison. Its size depends entirely on the black hole's mass, following a beautifully simple relationship that would make mathematicians weep with joy. The more massive the black hole, the larger its horizon, scaling in direct proportion like a cosmic recipe, where doubling the ingredients doubles the final product. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers, roughly the distance of a pleasant evening walk, except this particular walk would end with you being compressed into spaghetti and disappearing from the observable universe forever. But here's where things become deliciously strange. Larger black holes are actually less dangerous places to visit, at least initially. A supermassive black hole, the kind that lurks at the center of galaxies with the mass of millions or billions of suns, might have an event horizon hundreds of millions of kilometers across. That's larger than the orbit of Earth around the Sun, which means you could cross the event horizon of such a black hole without even realizing it had happened. You'd sail past this cosmic point of no return as casually as crossing an invisible line between countries, with no fanfare, no warning signs, no cosmic customs agents checking your passport to eternity. This counterintuitive gentleness of supermassive black holes comes from a principle that seems almost backwards. The gravitational forces at the event horizon are actually weaker for larger black holes. It's not that these giants are less massive, quite the opposite, but their mass is spread over such a vast area that the local gravitational gradient is surprisingly mild. Think of it like the difference between standing on a steep hill versus a gentle slope. Both might rise to the same height, but one will make your calves burn while the other feels like a casual stroll. The supermassive black hole is the cosmic equivalent of that gentle slope, at least until you get much closer to its center. Cross this threshold, and you've entered a realm where the normal rules of cause and effect start to blur in the most unsettling ways. Information can flow in but never out, creating what physicists call the information paradox, one of the deepest mysteries in modern physics. It's like a cosmic one-way mirror, where we can send messages in but never receive replies. A celestial post office with no return address, where letters disappear into an eternal dead letter office. Every phone call placed from inside an event horizon goes straight to voicemail. Every text message vanishes into the cosmic equivalent of a network dead zone. Every attempt at communication becomes a message in a bottle thrown into an ocean that has no shores. The event horizon also represents something profound about the nature of knowledge itself. Once something crosses this boundary, it becomes fundamentally unknowable to the rest of the universe. We can theorize about what happens inside, we can run computer simulations and solve equations, but we can never actually observe or verify what occurs beyond that invisible line. It's the ultimate limitation on scientific investigation, a boundary not just in space, but in the very possibility of knowledge. The universe has created a region where the scientific method hits an absolute wall, where hypothesis can never be tested by observation because observation itself becomes impossible. From the perspective of relativity, the event horizon is where time and space begin to play very strange games indeed. For an outside observer watching someone fall into a black hole, time dilation creates an almost surreal spectacle. The falling person appears to slow down dramatically as they approach the horizon, their movements becoming increasingly sluggish until they seem to freeze entirely at the boundary. Meanwhile, their light becomes redshifted to longer and longer wavelengths, making them appear redder and dimmer until they fade from view like a cosmic Cheshire cat, leaving behind only the gravitational grin of the black hole itself. But here's the really mind-bending part. From the perspective of the person falling in, none of this dramatic slowing occurs. They cross the event horizon in perfectly normal, finite time, completely unaware that the outside universe has aged millions or billions of years during their final approach. Their watch ticks normally. Their thoughts proceed at their usual pace. Their morning coffee would still taste the same if they happened to be sipping it during the fall. It's only the outside universe that experiences this temporal disconnect, watching their final moments stretched across eons like a cosmic slow-motion replay that never quite reaches its conclusion. The mathematics describing event horizons reveals something equally fascinating. They're not fixed objects, but dynamic boundaries that can grow but never shrink, at least according to classical physics. When matter falls into a black hole, the event horizon expands to accommodate the additional mass, like a soap bubble growing as you blow more air into it. When two black holes merge, their event horizons combine into a single, larger horizon, following precise mathematical rules that govern how area behaves in these extreme gravitational environments. It's cosmic accounting where the books must always balance, but only in one direction. This one-way growth of event horizons reflects a deeper principle about black holes and entropy. The area of an event horizon is directly related to the amount of entropy, or disorder, contained within the black hole. Since entropy can only increase according to the second law of thermodynamics, event horizons can only grow larger, never smaller. They're like cosmic savings accounts, where you can only make deposits, never withdrawals, accumulating entropy, the way a tree accumulates, rings, creating a permanent record of everything that has ever fallen past their boundaries. Perhaps most mysteriously, the event horizon might not be the simple, well-defined boundary it appears to be in our current theories. Some advanced theories in quantum gravity suggest that what we think of as a sharp event horizon might actually be a fuzzy, quantum mechanical boundary, where the distinction between inside and outside becomes probabilistic rather than absolute. These theories propose that information might leak out of black holes through quantum effects, like water slowly seeping through what appeared to be a perfectly waterproof dam. If true, it would mean that event horizons are more like one-way membranes than absolute barriers, allowing for the incredibly slow escape of information over astronomical timescales. The event horizon also serves as a cosmic laboratory for testing our most advanced theories about the nature of reality. It's the place where general relativity, quantum mechanics, and thermodynamics all come together in a complex dance that we're still learning to understand. Some physicists believe that studying event horizons theoretically will eventually lead us to a unified theory of quantum gravity, the holy grail of theoretical physics, that would finally reconcile our understanding of the very large with our understanding of the very small. In this sense, black hole event horizons aren't just astronomical objects, but fundamental features of reality that hold keys to unlocking the deepest secrets of how the universe works at its most basic level. As you approach a black hole, something rather uncomfortable called spaghettification begins to occur, and despite its playful name that sounds like it belongs in a cozy Italian restaurant, it's one of the universe's more unpleasant dining experiences. The gravitational force at your feet becomes noticeably stronger than at your head, since your feet are closer to the black hole's center by the length of your body. This difference in gravitational pull is called a tidal force, the same phenomenon that moves our oceans in their gentle twice-daily rhythm, but amplified to extraordinary and decidedly less gentle extremes. Your body would begin to stretch vertically and compress horizontally, like being gently pulled apart by an invisible cosmic taffy machine, operated by someone who's never quite mastered the art of gentle. The name spaghettification was coined by physicists who clearly had a sense of humor about the universe's more violent tendencies. It captures the essential process quite accurately. You become long and thin, like a piece of pasta being pulled from the cosmic colander of space-time. But unlike actual spaghetti, which maintains its essential spaghettiness throughout the stretching process, human bodies are rather less accommodating to this kind of geometric transformation. We're made of bones and muscles and various squishy bits that prefer to maintain their current arrangements. Thank you very much. The mathematics behind tidal forces is surprisingly elegant for such a destructive phenomenon. The gravitational force follows an inverse square law, meaning it gets stronger very quickly as you get closer to the source. When you're far from a black hole, the difference in gravitational pull between your head and feet is negligible, like the difference between being on the first floor versus the second floor of a building. But as you get closer, this difference becomes more pronounced, then dramatic, then eventually fatal. It's like the universe's way of enforcing a very strict dress code, where the only acceptable attire is an extremely elongated version of yourself. For stellar mass black holes, those formed from collapsed stars, this stretching becomes uncomfortable long before you reach the event horizon. Your body would begin to feel the differential forces while you're still thousands of kilometers away from the point of no return. First, you might notice a peculiar sensation in your spine, as if someone were very gently trying to make you taller. Then, this gentle stretching would become less gentle, more insistent, until your body could no longer maintain its structural integrity against the competing gravitational demands of your head wanting to fall slower than your feet. But here's where the universe shows its sense of cosmic irony. The larger the black hole, the more civilized the spaghettification process becomes. Those supermassive black holes lurking at galaxy centers are so enormous that you could cross their event horizons without experiencing any significant tidal forces at all. You might not even realize you'd passed the point of no return until well after the fact. It's as if the universe has decided that the bigger the gravitational monster, the better its table manners should be. You could have a perfectly pleasant tea and biscuits while crossing into eternal cosmic imprisonment. The compression aspect of spaghettification is often overlooked in favor of the more dramatic stretching, but it's equally important to the overall transformation. As you're pulled longer vertically, you're also squeezed narrower horizontally, like a cosmic stress ball being manipulated by invisible hands. This happens because the gravitational field doesn't just pull you toward the black hole, it also pulls the sides of your body toward the center line of your fall. Imagine falling feet first down a funnel that's slowly narrowing, except the funnel is made of warped space-time and the narrowing is happening to you rather than the tunnel. The timing of spaghettification depends dramatically on the mass of the black hole you're approaching. For a black hole with the mass of our Sun, you'd be thoroughly spaghettified long before reaching the event horizon, transformed into a very long, very thin stream of what used to be you, stretched across thousands of kilometers of space like cosmic silly putty. But for a supermassive black hole, you might pass through the event horizon, fall for hours or even days, and only then begin to notice the uncomfortable stretching sensations that herald your eventual transformation into human linguini. What makes this process particularly unsettling is that it's not sudden or dramatic like an explosion. It's gradual, progressive, a slow-motion dissolution of your bodily integrity that follows precise mathematical laws. Your molecules don't disappear or transform into exotic matter. They simply get rearranged into a much longer, thinner configuration than biology intended. Every atom remains accountable for. Every electron continues orbiting its nucleus. But the overall architecture of your existence gets remodeled according to the non-negotiable demands of curved space-time. The process also has interesting implications for consciousness and perception. Assuming your brain could somehow continue functioning during the early stages of spaghettification, your sensory experience would become increasingly strange. Your feet, being closer to the black hole, would experience time slightly slower than your head, creating a temporal gradient across your body. Your neural signals would have to travel across regions of space, experiencing slightly different rates of time, potentially creating the most unusual headache in the history of medicine. Eventually, of course, the stretching would disrupt neural function entirely, but for a brief period, you might experience the only naturally occurring case of temporal jet lag within a single body. Time plays wonderful tricks near black holes, becoming stretchy and unreliable like a clock made of warm honey that's been left too long in cosmic sunlight. As you fall toward the event horizon, time slows down dramatically relative to distant observers, creating one of the most mind-bending phenomena in all of physics. This isn't just theoretical speculation or mathematical curiosity. It's a real, measurable effect that fundamentally alters the nature of existence itself near these gravitational giants. To someone watching from far away, you would appear to slow down progressively, your movements becoming increasingly sluggish, as if you were swimming through cosmic molasses that gets thicker the deeper you go. The mathematics behind this temporal distortion is rooted in Einstein's general relativity, which revealed that time and space are not the fixed, absolute entities that Newton imagined, but rather flexible dimensions that respond to the presence of mass and energy. Near a black hole, where gravitational fields reach their most extreme values, these distortions become so pronounced that time itself becomes a variable quantity, flowing at different rates depending on your location in the curved space-time surrounding the gravitational monster. It's as if the universe has decided to operate multiple time zones in the same vicinity, except instead of neat hour-long differences, you get dramatic variations that can span millions of years. From the perspective of a distant observer safely watching from many thousands of kilometers away, your approach to the event horizon becomes an increasingly slow-motion spectacle. As you fall closer to the black hole, every second of your experience corresponds to longer and longer periods of time for the distant observer. What feels like a normal heartbeat to you might represent minutes or hours to someone watching from afar. Your final wave goodbye could appear to last for centuries from their perspective. A cosmic slow-motion replay that stretches toward infinity but never quite reaches its conclusion. This temporal stretching is accompanied by an equally dramatic effect on light itself. As photons climb out of the increasingly strong gravitational field to reach the distant observer, they lose energy and become redshifted. Their wavelengths stretch toward the red end of the spectrum and beyond. You would appear not just slower but also redder, your image fading through the colors of sunset toward infrared and eventually into radio waves that become too faint to detect. From the distant observer's perspective, you would gradually fade from view like a cosmic Cheshire cat, becoming redder and dimmer until you disappear entirely, frozen forever at the event horizon in their reference frame. But here's where the true strangeness of relativity reveals itself. From your perspective as the falling observer, none of this dramatic slowing occurs. Your watch ticks at its normal rate, your thoughts proceed at their usual pace, your morning coffee would still taste the same if you happened to be sipping it during the fall. Time passes normally for you, and you cross the event horizon in finite, measurable time, completely unaware that the outside universe has aged millions or billions of years during your final approach. It's like being the star of a movie that's being played in ultra-slow motion for everyone else, while you experience it at normal speed. This creates a profound disconnect between different reference frames, a fundamental aspect of relativity that challenges our intuitive understanding of simultaneous events. When you cross the event horizon, that crossing happens at a specific moment in your personal timeline, but it corresponds to an infinitely distant moment in the timeline of outside observers. In a very real sense, your crossing of the event horizon occurs both immediately and never, depending on whose clock you're using to measure time. It's as if the universe has created a temporal puzzle where the same event can be both completed and eternally pending. The implications of this time dilation extend far beyond the dramatic final moments of your fall. Even before reaching the event horizon, the effects become noticeable and increasingly pronounced. If you were somehow hovering at a fixed distance from a black hole, perhaps supported by a very powerful rocket engine, you would age more slowly than friends back on Earth. Time dilation near black holes isn't just a curiosity for falling objects. It affects anyone who ventures into the strong gravitational fields surrounding these cosmic giants. It's nature's version of a fountain of youth, though admittedly one with rather extreme membership requirements. This temporal distortion also affects the very nature of cause and effect near black holes. Signals sent from the infalling observer to the outside universe become increasingly redshifted and time-delayed, eventually fading beyond detection. Meanwhile, signals from the outside universe to the falling observer become blue-shifted and time-compressed, potentially creating a brilliant flash of radiation containing the entire future history of the outside universe compressed into the final moments before hitting the singularity. It's as if the cosmos has arranged for you to witness the end of everything just before experiencing your own personal ending. The mathematical beauty of time dilation near black holes lies in its precise predictability. Given the mass of a black hole and your distance from it, physicists can calculate exactly how much your time will differ from distant observers. This isn't guesswork or approximation. It's as reliable as calculating the area of a circle or the trajectory of a thrown ball. The universe follows these temporal rules with absolute consistency, creating a cosmic clockwork where time itself becomes a measurable, calculable dimension that varies according to precise mathematical relationships. Perhaps most remarkably, this time dilation represents one of the few places in physics where the passage of time itself becomes directly observable and measurable. In everyday life, we experience time as a constant flow, a steady background against which events unfold. But near black holes, time becomes a dynamic player in the cosmic drama, stretching and compressing according to the local gravitational environment. It transforms from an invisible stage where physics happens into a visible actor participating in the performance, making time itself one of the most fascinating characters in the black hole story. Falling into a black hole would provide the universe's most spectacular and final light show, a cosmic farewell performance that would make even the most elaborate fireworks display seem like a single birthday candle by comparison. As you approach the event horizon, you'd see the entire future history of the universe compressed into a brilliant flash behind you, while ahead, the black hole's interior remains mysteriously dark, like looking into the universe's most profound secret, while simultaneously witnessing its entire future unfold in accelerated time. This extraordinary visual experience comes courtesy of extreme gravitational time dilation and light-bending effects that transform your final journey into something resembling a cosmic IMAX theater with the most dramatic soundtrack the universe has ever composed. The physics behind this spectacular display involves the interaction between gravity, light, and time in ways that create natural special effects more impressive than anything Hollywood could imagine. As you fall inward, light from the outside universe gets blue-shifted toward higher energies due to your motion through the black hole's gravitational field. Simultaneously, the extreme time dilation means that what appears as the normal passage of time to distant observers becomes compressed into shorter and shorter intervals from your perspective. The combination of these effects creates a situation where millions or billions of years of cosmic history get squeezed into the final moments of your fall, all the light from the future universe cascading toward you in an increasingly energetic torrent. Behind you, this compression of time and blue shifting of light would create what physicists poetically call the blue flash of doom, a brilliant ring of radiation containing light from stars that won't be born for millions of years, galaxies that have yet to form, and cosmic events that the outside universe hasn't even begun to imagine. You'd witness the birth and death of countless stars compressed into moments, the formation and collision of galaxies speeding past like cosmic time-lapse photography, the gradual cooling and expansion of the universe playing out in fast-forward, as if someone had pressed the universe's cosmic fast-forward button and forgotten to let go. The visual effects would be unlike anything your eyes have evolved to process. Starlight from across the cosmic horizon would be gathered and focused by the black hole's gravity, creating brilliant caustics and light patterns that dance across your field of view like aurora painted with the light of distant suns. The black hole itself acts as a gravitational lens, bending and focusing light in ways that could theoretically allow you to see around the cosmic horizon, glimpsing regions of the universe that would normally be forever hidden behind the curvature of space-time. It's as if the universe has arranged for your final moments to include a guided tour of cosmic geography that no telescope could ever provide. However, this cosmic light show comes with a rather significant catch that somewhat dampens the sightseeing experience. The same blue-shifting process that creates these beautiful visual effects also transforms relatively harmless starlight into increasingly energetic radiation. Visible light gets shifted into ultraviolet, then X-rays, then gamma rays of such intensity that they would likely cook you thoroughly before you could fully appreciate the cosmic cinematography. The universe's most beautiful sight might also be its most lethal, like being offered front-row seats to a supernova with no protective eyewear or radiation shielding available. The intensity of this radiation increases dramatically as you approach the event horizon, following mathematical laws that are as precise as they are unforgiving. What starts as a gentle brightening of the cosmic background gradually builds to a crescendo of high-energy photons that would make standing next to a nuclear reactor seem like a relaxing day at the beach. It's the universe's way of ensuring that even if the spaghettification doesn't get you first, the radiation certainly will, providing multiple backup plans for your cosmic demise with the thoroughness of a belt-and-suspenders approach to gravitational safety. Ahead of you, toward the black hole's interior, the view would be quite different and considerably more mysterious. The event horizon itself would appear as a perfect sphere of absolute darkness, darker than the darkest night you've ever experienced, darker than closing your eyes in a windowless room, darker than the concept of darkness itself. No light emerges from beyond that boundary, creating a perfect silhouette against the brilliant radiation show happening behind you. It's like looking into a hole cut out of reality itself, a cosmic void that represents the complete absence of information rather than simply the absence of light. This darkness ahead isn't empty space or the normal blackness between stars, but rather the complete cutoff of information flow from the black hole's interior. Every photon that has ever crossed the event horizon is trapped forever behind that boundary, unable to escape and tell you what lies within. You're approaching the universe's ultimate information firewall, a boundary beyond which no knowledge can return. The darkness you see isn't the darkness of an unlit room, but the darkness of unknowability itself, the cosmic equivalent of a permanently closed book written in a language that can never be translated. The transition between the brilliant light show behind you and the perfect darkness ahead would be incredibly sharp, like standing at the edge between day and night, except the day contains the entire future history of the universe, and the night represents the complete unknown. This stark contrast would make the event horizon visible as a perfect geometric boundary, a sphere of pure black set against the cosmic fireworks display. As you cross this boundary, the light show behind you would cut off abruptly, not fading gradually but stopping instantly, like someone switching off the universe's most spectacular display, just as you're no longer able to share the experience with anyone else. Once inside the event horizon, you've entered a realm where space and time exchange some of their familiar roles, in the most unsettling cosmic role reversal imaginable, like actors in a play who've suddenly decided to swap parts halfway through the performance without telling the audience. The center of the black hole, called the singularity, lies not somewhere ahead of you in space, but rather ahead of you in time, making it as inevitable as next Tuesday, but considerably more dramatic in its arrival. It's as inevitable as aging, as certain as the sunrise, but compressed into a time frame that makes both of those processes seem leisurely by comparison. This fundamental shift in the nature of space and time represents one of the most profound departures from normal physics anywhere in the universe. In the familiar world outside black holes, space and time maintain their traditional roles with the reliability of old friends who always show up when expected. You can move freely in 3 dimensions of space while being carried forward inexorably through time, like riding a cosmic escalator that only moves in the temporal direction while allowing you to walk around freely on its spatial platform. But inside an event horizon, the mathematics of curved spacetime creates a situation where the radial direction toward the center becomes time-like rather than space-like, fundamentally altering the relationship between cause and effect, motion and destiny. This means that every path through spacetime now leads to the singularity, not as a destination you might choose to visit, but as a temporal inevitability you cannot avoid any more than you can avoid experiencing next Thursday. There's no steering away, no changing course, no cosmic GPS that can calculate an alternate route to your destination. The singularity isn't just your destination, it's your inevitable future, approaching whether you like it or not, with the persistence of gravity and the certainty of mathematics. It's like being inside a cosmic funnel where all roads lead to the center, except the roads are made of time itself, and the center is a point where physics admits it has no idea what happens next. The geometry of spacetime inside the event horizon becomes so twisted that the normal concepts of direction lose their meaning in profound ways. Moving away from the singularity becomes as impossible as moving backward in time, not because of any force preventing you, but because the structure of spacetime itself no longer contains any paths that lead in that direction. It's like trying to find north while standing exactly at the North Pole, or attempting to go further east while standing on the international date line. The direction you want to go simply doesn't exist within the geometric structure of your reality. This inevitable march toward the singularity occurs within a time frame that depends on the black hole's mass and your current distance from the center. For a stellar mass black hole, you might have microseconds to contemplate your situation before reaching the singularity, while for a supermassive black hole, you could potentially have hours or even days to ponder the philosophical implications of your predicament. The universe provides you with time to think about your fate in proportion to the size of the gravitational monster that sealed it, which seems either remarkably considerate or particularly cruel, depending on your perspective on existential contemplation. The experience of falling toward an inevitable future singularity would be unlike anything else in human experience, combining the certainty of fate with the mystery of the unknown. You know exactly where you're going and approximately when you'll arrive, but you have absolutely no idea what will happen when you get there. It's like having a ticket to a destination that's not on any map, with a departure time printed clearly, but an arrival experience that transcends all previous human understanding of arrival experiences. During this inevitable journey, the geometry of space around you would become increasingly strange in ways that challenge basic intuitions about shape and distance. Tidal forces would grow stronger, space itself would become more curved, and the familiar Euclidean geometry of everyday life would give way to something far more exotic. The mathematical description of your situation would involve terms and concepts that sound more like poetry than physics. Geodesics, curvature tensors, and metric signatures that describe a reality where space and time dance together in ways that would make a mathematician weep with either joy or despair. The psychological impact of this temporal inevitability might be the most challenging aspect of the entire experience. In normal life, the future maintains at least the illusion of uncertainty, the comforting ambiguity that allows hope and planning, and the general assumption that tomorrow might be different from today. But inside an event horizon, the future becomes geometrically predetermined with mathematical precision. Your future isn't just likely or probable, it's encoded in the structure of space-time itself with the certainty of a theorem. Yet even as space and time perform their cosmic role reversal, some aspects of physics continue to behave normally, creating an island of familiar physical laws within an ocean of geometric strangeness. Your mass remains constant, your energy is conserved, and the basic chemical bonds that hold your body together continue to function according to their usual electromagnetic rules, at least until the tidal forces become too extreme. It's as if the universe has decided to maintain some aspects of normalcy, even while fundamentally restructuring the relationship between space and time. This preservation of some physical laws while others undergo dramatic transformation creates a unique environment where the familiar and the impossible coexist. You might still be able to check your watch and find it ticking normally, even while that watch is counting down to a collision with a mathematical singularity where time itself might cease to have meaning. It's the ultimate cosmic contradiction. Experiencing normal time while approaching a place where time might end. Following familiar physical laws while approaching a point where those laws admit complete ignorance about what happens next. At the heart of every black hole lurks something that makes physicists deeply uncomfortable, more uncomfortable than wearing socks with sandals to a formal dinner or trying to explain quantum mechanics to someone who thinks atoms are a suggestion rather than reality. This cosmic troublemaker is called a singularity, a point where matter is compressed to infinite density and space-time curvature becomes infinite, which is mathematics' polite way of saying, we haven't the foggiest idea what's happening here, and our equations have decided to take an extended coffee break. It's the place where our most sophisticated theories about the universe simply throw up their hands, declare intellectual bankruptcy, and suggest, perhaps, we should try a different career path. Maybe something in accounting where infinities are less problematic. The mathematical description of a singularity reads like a cosmic joke played by the universe on anyone trying to understand it. Density becomes infinite, which means that a finite amount of matter occupies zero volume, creating a ratio that would make any calculator display an error message and possibly file a complaint with the mathematics department. Space-time curvature also becomes infinite, meaning that the gentle hills and valleys of Einstein's geometric description of gravity become vertical cliffs that extend infinitely upward, like a cosmic landscape designed by someone with absolutely no concern for building codes or the comfort of theoretical physicists trying to navigate the terrain. Our current theories simply break down at the singularity, like a GPS trying to navigate a landscape that doesn't exist, or a weather forecast attempting to predict conditions inside a tornado made of pure mathematics. General relativity, which works beautifully everywhere else in the universe, from predicting planetary orbits to describing the expansion of space itself, encounters the singularity, and essentially admits defeat with the grace of a chess grandmaster facing an opponent who somehow managed to place 17 queens on the board simultaneously. The equations that normally provide precise, reliable predictions suddenly start producing infinities, and infinities in physics are nature's way of saying, "You're asking the wrong question." This mathematical breakdown isn't just an academic inconvenience, or a minor glitch in our understanding that could be fixed with better computers or stronger coffee. It represents a fundamental limitation in our current description of reality, a cosmic "here be dragons" marked on the map of space-time where our best theories fear to tread. The singularity is where the smooth, predictable universe of Einstein's relativity meets something so extreme that it transcends the mathematical framework that describes everything else, from the orbit of electrons around atomic nuclei to the dance of galaxies across cosmic time. Some physicists hope that quantum effects might smooth out this infinite weirdness, like cosmic sandpaper applied to the rough edges of mathematical impossibility. These theories propose something called a quantum bounce, where matter approaching infinite density would somehow rebound before reaching the true mathematical singularity, perhaps creating a highly compressed but finite state that our equations could handle without having nervous breakdowns. It's like suggesting that the universe has a built-in safety mechanism that prevents mathematics from becoming completely unreasonable, a cosmic circuit breaker that trips before the calculations become infinitely problematic. Other theoretical approaches suggest that the singularity might represent the birth of new regions of space-time, cosmic seeds from which baby universes might sprout like strange fruit growing on the tree of hyperspace. In these models, what appears to be the end point of gravitational collapse might actually be a beginning, a cosmic recycling center where matter and energy get processed into entirely new realities. It's an appealingly poetic idea that turns the apparent finality of singularities into a kind of cosmic reproduction, where black holes become the universe's way of creating new domains of existence. Still, others wonder if the question of what happens at the singularity is even meaningful, like asking what's north of the North Pole or what happened before the beginning of time. Some interpretations of quantum gravity suggest that space-time itself might have a granular structure at the smallest scales, made up of discrete units that prevent the infinite compression required for true singularities. In this view, the singularity is like a mathematical mirage that disappears when you get close enough to see it clearly, replaced by something finite and comprehensible, though possibly still quite strange. The mystery of the singularity also touches on fundamental questions about the nature of information and the structure of reality itself. If matter and energy can be compressed to infinite density, what happens to all the information they contain? Does the complete history of every atom that ever fell into the black hole get compressed into an infinitely small point, creating a cosmic library where all the books have been squeezed down to mathematical points? Or does the information somehow transform into something entirely different, perhaps leaking out through quantum processes that we don't yet understand? Perhaps most unsettling of all, the singularity represents a place where the universe simply says, "That's quite enough physics for one day," and declares a permanent recess from the laws that govern everything else. It's cosmic anarchy disguised as mathematics, a region where the orderly universe of cause and effect, conservation laws, and predictable behaviors gives way to something that transcends our current understanding of what it means for something to exist. The singularity isn't just strange. It's the place where strangeness itself becomes insufficient to describe what might be happening, leaving us with the humbling realization that the universe contains regions where even our strangest theories become as inadequate as a paper umbrella in a hurricane made of pure impossibility. Not all black holes are created equal, and they come in several cosmic flavors that range from the merely terrifying to the absolutely stupendous, like a cosmic ice cream shop specializing in gravitational extremes, where every option comes with a side of existential dread. The smallest and most common variety are stellar mass black holes, the cosmic equivalent of the neighborhood corner store of gravitational collapse, typically weighing between 5 and 50 times our sun's mass. These are the black holes formed from the dramatic deaths of massive stars, the ones that announce their presence with supernova explosions visible across galactic distances before settling down to their new careers as invisible gravitational monsters lurking in the cosmic shadows. These stellar mass black holes are relatively compact, with event horizons that could fit comfortably within a large city, though admittedly it would be a city with rather unusual real estate values and a complete absence of property insurance coverage. They represent the minimum viable product of black hole formation, the smallest possible configuration where matter can successfully achieve the cosmic goal of disappearing entirely from the observable universe. Their gravitational fields are intense and localized, creating cosmic neighborhoods where the tidal forces become lethal within a few thousand kilometers, making them decidedly inhospitable to anyone hoping for a close encounter with extreme physics. Then there are intermediate mass black holes, the mysterious middle children of the black hole family, weighing hundreds to thousands of solar masses and causing astronomers considerable frustration because they're harder to find and study than their smaller and larger relatives. These cosmic teenagers seem to exist in that awkward phase between stellar collapse and supermassive growth, neither small enough to form easily from single stellar deaths, nor large enough to dominate galactic centers with obvious gravitational authority. They lurk in globular clusters and the outskirts of galaxies like cosmic wallflowers, significant enough to warp space-time dramatically but shy enough to avoid the astronomical spotlight. The formation mechanisms for intermediate mass black holes remain one of astronomy's ongoing mysteries, like trying to solve a jigsaw puzzle when half the pieces are invisible and the other half keep changing shape. They might form from the collision and merger of smaller black holes, cosmic accidents where stellar mass black holes decide to pool their gravitational resources and create something larger than the sum of their parts. Alternatively, they could be the remnants of the universe's first generation of stars, hypothetical giants that were hundreds of times more massive than anything we see today, stellar behemoths that lived fast and died young in the cosmic equivalent of rockstar excess. At the cosmic extreme, we find supermassive black holes lurking at galaxy centers like gravitational emperors holding court over billions of stellar subjects, weighing millions to billions of solar masses, and making everything else in their galaxies seem quaint by comparison. These cosmic giants are so massive that their event horizons can span distances larger than planetary orbits, creating gravitational domains where you could host entire solar systems within their points of no return. They're the universe's ultimate examples of cosmic inflation, not the rapid expansion of space itself, but the expansion of gravitational influence to galactic proportions. Curiously, the larger the black hole, the gentler the ride becomes, at least initially, like the difference between falling off a cliff and gently rolling down a hill that happens to be infinitely deep. You could cross the event horizon of a supermassive black hole without immediately noticing, like stepping across an invisible threshold into another country, where the only difference is that you can never return home. The tidal forces at the event horizon are relatively mild, spread out over such vast distances that your body wouldn't feel the stretching effects until you've fallen much deeper into the gravitational well, possibly giving you hours or days to contemplate your cosmic predicament in relative comfort. This inverse relationship between black hole size and local danger seems almost counterintuitive, like discovering that the largest predators are actually the gentlest, but it follows naturally from the mathematics of curved space-time. The gravitational field strength at the event horizon depends not just on the black hole's mass, but also on the distance from its center, and larger black holes have proportionally larger event horizons. It's cosmic geometry working in your favor, at least temporarily, providing more spacious accommodations for your final journey into gravitational exile. The supermassive black holes also play crucial roles in galaxy formation and evolution, acting as cosmic regulators that control the rate of star formation and the overall structure of their galactic neighborhoods. They're not just passive gravitational sinks, but active participants in galactic ecology, occasionally feeding on nearby matter and releasing tremendous amounts of energy in the form of jets and radiation that can influence star formation across millions of light years. It's cosmic urban planning on the largest possible scales, where black holes serve as both city centers and zoning commissions, determining where and when new stellar neighborhoods can develop. The relationship between black hole mass and galactic properties suggests a deep connection between these gravitational monsters and the cosmic structures they inhabit. Galaxies and their central black holes seem to grow together over cosmic time, maintaining proportional relationships that hint at feedback mechanisms operating across vast scales of space and time. The black hole feeds on the galaxy's matter, while the galaxy provides the raw material for black hole growth, creating a cosmic symbiosis that shapes the large-scale structure of the universe itself. It's a partnership between the visible and invisible, the stellar and the gravitational, that demonstrates how black holes are not cosmic outliers but integral components of the universe's organizational structure. Most black holes in the universe are probably spinning, having inherited angular momentum from their stellar parents like cosmic heirlooms passed down through gravitational generations, except these particular family treasures happen to warp space-time in the most dramatic possible ways. These rotating black holes, called Kerr black holes after the mathematician Roy Kerr who first solved Einstein's equations for spinning massive objects, are far more complex than their stationary cousins, like comparing a simple spinning top to a cosmic hurricane made of curved space-time that's decided to choreograph its own dance with the fundamental forces of reality. The spinning mass drags space-time around with it in a phenomenon aptly called frame dragging, creating a region where space itself is forced to rotate, whether it wants to or not. This dragging of space-time creates a truly bizarre region called the ergosphere, a cosmic zone where the normal rules of standing still become physically impossible, like trying to remain motionless while standing on a cosmic conveyor belt that's made of space and time themselves. Inside the ergosphere, you couldn't remain stationary, even if you tried with the most powerful rocket engines imaginable, because space-time itself carries you along like a cosmic current that flows around the spinning black hole. It's as if the universe has created a region where the concept of not moving has been temporarily suspended by management, leaving you with no choice but to participate in the black hole's rotational dance, whether you're in the mood for dancing or not. The ergosphere extends beyond the event horizon, creating a layered structure around rotating black holes that resembles cosmic Russian dolls, each nested boundary with its own peculiar properties and gravitational etiquette. The outer boundary of the ergosphere is called the static limit, beyond which you can still hover motionless if you have sufficient rocket power and an inexplicable desire to spend your fuel budget fighting against curved space-time. But cross this invisible line inward, and you're committed to rotating along with the black hole's spin, though you can still escape to the outside universe if you're clever about your trajectory and have enough energy reserves for the cosmic equivalent of swimming upstream. This rotation also means that Kerr black holes have two event horizons rather than one, like cosmic security checkpoints with different levels of gravitational clearance required for entry. The outer event horizon is the familiar point of no return that we've come to know and love in our discussions of black hole boundaries. But spinning black holes also possess an inner event horizon that creates additional layers of complexity in the already complicated geometry of curved space-time. Between these two horizons lies a region called the inner ergosphere, where the mathematics become so intricate that even physicists sometimes pause to take aspirin before continuing their calculations. The space between the inner and outer event horizons creates what might be the strangest neighborhood in the universe, a region where you've already passed the point of no return but haven't yet reached the final point of no return. Like being trapped in cosmic bureaucracy, where there are multiple forms to fill out before you can complete your journey to oblivion. The physics in this region involves concepts that sound more like abstract art than science: closed time-like curves, negative energy densities, and causal structures that would make a logic professor weep with either admiration or despair, depending on their philosophical orientation toward paradoxes. The rotation rate of a black hole is limited by physics itself, preventing these cosmic dancers from spinning so fast that they tear themselves apart or create naked singularities that would violate the cosmic censorship hypothesis. This speed limit, known as the extremal limit, ensures that rotating black holes maintain their event horizons and keep their singularities properly hidden behind gravitational curtains, like cosmic strippers who maintain appropriate levels of mathematical modesty. A black hole spinning at the maximum possible rate would have its inner and outer event horizons merge into a single surface, creating what physicists call an extremal black hole, though whether such perfectly spinning objects actually exist in nature remains an open question. The ergosphere of a rotating black hole also enables one of the most remarkable theoretical processes in all of physics: The Penrose process, named after physicist Roger Penrose, who discovered that you can actually extract energy from a spinning black hole by dropping objects into the ergosphere and retrieving them with more energy than they started with. It's like cosmic shoplifting, where you steal energy from the black hole's rotation, though the theft is perfectly legal according to the laws of physics, and the black hole doesn't seem to mind losing a bit of its spin in exchange for your continued existence in a slightly higher energy state. This energy extraction process works because the ergosphere allows for the existence of particles with negative energy as measured by distant observers, creating a situation where dropping something into the black hole can actually increase the total energy of everything outside the black hole. It's cosmic accounting where the books balance in ways that seem impossible but are perfectly consistent with general relativity, like discovering that your bank account increases every time you make a withdrawal, except the bank is a rotating black hole, and the currency is angular momentum, stolen from the fundamental structure of space-time itself. The practical applications of the Penrose process remain entirely theoretical, since it requires precise navigation through regions of space-time where tidal forces would likely disassemble any spacecraft long before it could complete the energy extraction maneuver. But the mere fact that such processes are possible in principle demonstrates the remarkable richness of physics near rotating black holes, where the familiar concepts of energy conservation and thermodynamics take on new and sometimes counterintuitive meanings that challenge our basic assumptions about how the universe organizes its cosmic economy. Stephen Hawking discovered something wonderfully paradoxical about black holes that would make them simultaneously the universe's most perfect absorbers and its most patient cosmic evaporators, like discovering that the ultimate vacuum cleaner is also secretly a very slow leak. Black holes aren't perfectly black after all, but emit radiation and slowly evaporate like cosmic ice cubes melting in the warmth of empty space, though at a rate so glacial that it makes geological time seem hurried by comparison. This Hawking radiation emerges from quantum effects near the event horizon, where the violent fluctuations of space-time at the smallest scales create particle pairs that normally annihilate each other, but occasionally get separated by the black hole's gravitational field, allowing one particle to escape while its partner falls inward to contribute to the black hole's mass. The mechanism behind Hawking radiation involves the strange world of quantum mechanics, where empty space isn't actually empty, but filled with virtual particle pairs, constantly popping into existence and annihilating each other in a cosmic dance of creation and destruction that happens so quickly that we normally 22 can't observe it directly. Near a black hole's event horizon, this quantum foam becomes relevant to macroscopic physics in ways that would make both quantum theorists and relativity experts simultaneously excited and slightly nervous. When virtual particles appear near the event horizon, the intense gravitational field can separate them before they have a chance to annihilate, promoting them from virtual possibilities to real particles with genuine existence and measurable properties. The escaping particle carries away positive energy, while its partner that falls into the black hole carries negative energy as measured by distant observers, creating a situation where the black hole actually loses mass energy, even as it gains particles. It's cosmic bookkeeping that follows the strict rules of energy conservation while producing results that seem intuitively backwards, like a bank account that decreases every time you make a deposit. The black hole pays for the creation of real particles by sacrificing some of its own mass, gradually shrinking over astronomical timescales through this quantum mechanical bleeding of energy into the surrounding space. This evaporation process is incredibly faint for any black hole you're likely to encounter in the universe's current cosmic neighborhood. A stellar mass black hole would take longer than the age of the universe to evaporate completely, making it essentially eternal by any human standard of measurement, and giving you plenty of time to finish whatever projects you might have started before the black hole finishes its slow-motion disappearing act. The temperature of Hawking radiation from such black holes is lower than the cosmic microwave background radiation left over from the Big Bang, meaning they actually absorb more energy from their surroundings than they emit, growing slightly larger rather than smaller in today's universe. Paradoxically, smaller black holes evaporate faster than large ones, following an inverse relationship that seems almost vindictive in its mathematical precision. A black hole, the mass of a marble, would explode almost instantly with the energy of millions of hydrogen bombs, creating a cosmic firework display that would be spectacular but extremely brief and decidedly unhealthy for anyone in the immediate vicinity. This inverse relationship between size and evaporation rate means that the universe's smallest possible black holes would be its most energetic and short-lived, while the cosmic giants that dominate galactic centers will persist long after the last stars have burned out and the universe has cooled to near absolute zero. The energy spectrum of Hawking radiation follows a perfect black-body curve, the same mathematical distribution that describes the light from stars, the glow of hot coals, and the cosmic microwave background itself. This universality suggests something profound about the relationship between gravity, thermodynamics, and quantum mechanics, as if black holes are cosmic thermometers that reveal fundamental connections between seemingly unrelated areas of physics. The temperature depends inversely on the black hole's mass, so larger black holes are actually colder than smaller ones, creating a cosmic hierarchy where gravitational giants are thermal pygmies and quantum-scale black holes would burn with temperatures exceeding those found in stellar cores. The discovery of Hawking radiation revolutionized our understanding of black hole physics by revealing that these cosmic monsters have temperatures and can reach thermal equilibrium with their surroundings, behaving like exotic but comprehensible thermodynamic objects rather than purely gravitational abstractions. This thermal behavior implies that black holes have entropy, a measure of their internal disorder, which turns out to be proportional to the area of their event horizons, rather than their volume. It's as if all the information about what's inside a black hole is somehow encoded on its surface, like a cosmic hard drive where the storage capacity depends on surface area rather than internal volume. This connection between black hole area and entropy leads to profound questions about the nature of information and the fundamental limits of knowledge in our universe. If black holes can evaporate completely through Hawking radiation, what happens to all the information that fell into them over their cosmic lifetimes? Does it get destroyed, violating quantum mechanics' sacred principle that information cannot be lost? Or does it somehow escape through the radiation, encoded in subtle correlations that would take longer than the age of the universe to decode? This information paradox remains one of theoretical physics' most challenging puzzles, forcing physicists to reconsider basic assumptions about causality, locality, and the nature of reality itself. The evaporation process also raises fascinating questions about the ultimate fate of the universe itself. In the far future, after stars have burned out and galaxies have dispersed, black holes will be among the last remaining objects in an increasingly cold and empty cosmos. Their slow evaporation through Hawking radiation will represent one of the final sources of energy in a universe approaching maximum entropy, providing the last warm glow before everything settles into thermal equilibrium at absolute zero. It's the universe's way of ensuring that even its most permanent-seeming features eventually fade away, following cosmic recycling programs that operate on timescales that make geological ages seem like brief moments in an eternal process of creation and dissolution. Black holes create one of physics' deepest puzzles, a cosmic riddle that keeps theoretical physicists awake at night, contemplating the fundamental nature of reality itself, like insomniacs wrestling with the universe's most stubborn philosophical questions. The puzzle centers on what happens to information that falls into a black hole, and it's called the information paradox, though calling it a paradox makes it sound more like a clever word puzzle rather than a crisis that threatens to undermine our basic understanding of how the universe processes and preserves knowledge. Quantum mechanics insists that information cannot be destroyed, a fundamental conservation law as sacred and inviolable as the conservation of energy or momentum, suggesting that the universe maintains perfect records of everything that has ever happened, like a cosmic librarian with infinite storage space and absolutely no tolerance for lost books. But general relativity suggests that anything falling into a black hole is lost forever, creating what appears to be a direct contradiction between two of our most successful theories about how reality operates at its deepest levels. It's like discovering that your two most trusted friends have been telling you completely different stories about the same events, and now you have to figure out which one is lying, or whether they're both describing different aspects of a truth too complex for either to capture completely. The information that falls into a black hole seems to disappear permanently behind the event horizon, cut off from the rest of the universe by the fundamental geometry of curved space-time that prevents any information from escaping back to the outside world. This creates a cosmic accounting problem where the universe's books don't balance, violating the principle of unitarity that requires all quantum mechanical processes to be reversible in principle, even if they're practically impossible to reverse. If you throw a book into a fire, the information in the book isn't really destroyed, but gets scrambled into the complex patterns of smoke, ash, and heat radiation that contain all the original information in an extremely difficult-to-decode form. But if you throw the same book into a black hole, general relativity insists that the information disappears completely when the black hole eventually evaporates through Hawking radiation, creating a situation where the universe permanently loses track of part of its own history. Some theories propose that information is somehow encoded on the black hole's surface, stored in microscopic quantum fluctuations at the event horizon, like a cosmic hard drive, where data gets written in the language of curved space-time geometry. This holographic principle suggests that all the information about a black hole's interior can be stored on its two-dimensional surface, much like how a hologram can contain three-dimensional information on a flat piece of film. It's as if the universe has developed the ultimate data compression algorithm, capable of storing the complete description of a three-dimensional volume of space in the quantum structure of its boundary, though accessing this information would require computational capabilities that make current supercomputers look like pocket calculators from the Stone Age. Other theories suggest that information leaks out through Hawking radiation in subtle correlations between particles that escape over astronomical timescales, like cosmic messages written in a code so complex that deciphering them would take longer than the current age of the universe. In this view, the information isn't lost, but gets encoded in the quantum entanglement patterns between particles that emerged from the black hole at different times, creating a cosmic cryptography problem where the message is scattered across billions of years of radiation. The information would still be conserved technically, but retrieving it would require collecting and analyzing every photon emitted by the black hole throughout its entire evaporation process, a task that makes finding a needle in a haystack seem trivial by comparison. Recent developments in theoretical physics have led to even more exotic proposals, including the idea that black holes might be connected to other regions of spacetime through quantum wormholes, creating hidden pathways through which information might escape without violating the apparent laws governing event horizons. These quantum tunnels wouldn't be the macroscopic wormholes of science fiction, but microscopic connections operating at the smallest scales of spacetime geometry, where quantum mechanics and general relativity engage in their most intimate and confusing interactions. The information wouldn't escape in any conventional sense, but might leak into parallel regions of spacetime through quantum mechanical processes that operate below the threshold of classical physics. The information paradox also touches on fundamental questions about the nature of time and causality in quantum mechanical systems. If information can neither be created nor destroyed, then the current state of the universe must contain complete information about all its possible past and future states, creating a block universe picture where all of history exists simultaneously in the quantum mechanical description of reality. But black holes seem to create regions where this temporal symmetry breaks down, where the past can influence the future through information falling in, but the future cannot influence the past through information coming out. Some physicists have proposed that the paradox might be resolved by recognizing that the interior of a black hole doesn't exist in the usual sense, but is instead a holographic projection created by the complex quantum entanglement structure of the matter that formed the black hole and the Hawking radiation it emits. In this view, there is no actual interior beyond the event horizon, just a very convincing quantum mechanical simulation that preserves all the information while appearing to hide it behind a gravitational barrier. It's like discovering that the locked room you've been trying to peer into doesn't actually exist, But the lock and door are so convincing that they create the perfect illusion of hiding something that was never really there in the first place. Black holes have long captured imaginations as potential doorways to other parts of the universe, or even other universes entirely, serving as cosmic gateways in countless science fiction stories where intrepid explorers use them as shortcuts through the galaxy like interstellar subway stations with rather extreme entry requirements. The mathematics of general relativity does allow for exotic solutions called wormholes, hypothetical tunnels, connecting distant regions of space-time that would theoretically permit travel across vast, cosmic distances without the inconvenience of spending millions of years in transit at subluminal speeds. These mathematical constructs emerge naturally from Einstein's equations when you solve them for certain exotic configurations of matter and energy, creating geometric bridges that span space and time in ways that would make conventional navigation seem quaint and inefficient. However, such passages would likely collapse instantly unless held open by exotic matter with negative energy density, something we've never observed in nature and may not exist anywhere in the universe except in the fevered imaginations of theoretical physicists, trying to solve mathematical equations that seem determined to mock our engineering limitations. This exotic matter would need to violate the energy conditions that normal matter obeys, possessing properties that are not just unusual but fundamentally opposite to everything we understand about how energy and matter behave in our corner of reality. It's like needing construction materials that weigh less than nothing and push instead of pull, materials that would make the engineering challenges of building bridges across ordinary chasms seem simple by comparison. Even if stable wormholes existed and could be kept open by exotic matter that somehow circumvents the normal rules of physics, traveling through one connected to a black hole would be extraordinarily dangerous, like threading a needle while riding a roller coaster in a hurricane made of curved space-time and tidal forces. The gravitational environment near black holes creates conditions that would likely destroy any spacecraft long before it could successfully navigate through a hypothetical wormhole entrance, turning cosmic exploration into cosmic disintegration with the efficiency of a cosmic blender operating at relativistic speeds. The theoretical wormholes that emerge from general relativity come in various exotic flavors, each with their own particular brand of impossibility and engineering challenges. Traversable wormholes would require not just exotic matter but specific configurations that maintain stability while allowing matter and information to pass through safely, like cosmic tunnels that need to remain rigid despite being made of warped space-time. The amount of exotic matter required would likely exceed the mass of several stars, creating the cosmic equivalent of using a nuclear reactor to power a flashlight, assuming you could somehow acquire nuclear reactors that run on matter that doesn't exist. Einstein-Rosen bridges, the original wormhole solutions discovered in the early days of general relativity, would collapse too quickly for any signal to pass through, much less a spacecraft full of explorers hoping to discover new cosmic neighborhoods. These theoretical bridges exist for such brief moments that even light, traveling at the universe's ultimate speed limit, couldn't make the journey from one end to the other before the entire structure collapsed into disconnected regions of space-time. It's like trying to cross a bridge that demolishes itself faster than you can run, except the bridge is made of geometry itself, and running requires traveling at the speed of light through regions where space and time have decided to behave in completely unreasonable ways. The universe seems to make cosmic shortcuts tantalizingly possible in theory, but practically impossible in reality. Like a cosmic bureaucracy that issues permits for interstellar travel through wormholes, but requires documentation that can only be obtained from planets that don't exist, using technologies that violate fundamental physical laws. Even the most optimistic theoretical scenarios for wormhole travel require engineering capabilities that make our current space technology look like stone tools, involving the manipulation of space-time geometry on scales that would require energy sources comparable to entire stars and construction techniques that presuppose mastery over forms of matter that may be purely mathematical fantasies. Recent theoretical work has suggested that quantum effects might stabilize certain types of wormholes, creating microscopic tunnels through space-time that could theoretically allow information to pass between distant regions without requiring exotic matter. These quantum wormholes would be far too small for macroscopic travel, but might permit the transfer of quantum information through processes that operate at the intersection of general relativity and quantum mechanics. It's like discovering that the universe provides cosmic postal service for letters written in quantum mechanical code, though the delivery time might exceed the age of the universe, and the letters would need to be written in a language that doesn't technically exist. The connection between black holes and wormholes in theoretical physics has led to fascinating speculations about the nature of space-time connectivity and the possibility that our universe might be riddled with hidden passages that connect distant regions through higher dimensional shortcuts. Some theories propose that black holes might naturally create wormhole connections to other black holes, creating a cosmic network of gravitational tunnels that spans the universe like a subway system designed by entities with a very different understanding of practical transportation engineering. Perhaps most intriguingly, some recent theoretical work suggests that the interiors of black holes might be connected through quantum entanglement to other regions of space-time, creating information pathways that don't require classical wormholes but operate through purely quantum mechanical connections. These quantum bridges wouldn't allow for conventional travel but might permit the transfer of information through processes that transcend our usual understanding of locality and causality. It's cosmic telecommunications through quantum entanglement, like having a telephone that works by sharing quantum states with distant regions of the universe. Assuming you don't mind phone calls that take longer than cosmic ages to complete and carry information in forms that require quantum computers the size of galaxies to decode properly. For most of human history, black holes remained purely theoretical, cosmic ghosts detectable only through their gravitational influence on nearby matter, like trying to study invisible dancers by watching their partners' movements in a cosmic ballroom where half the participants refuse to wear anything that reflects light. These gravitational phantoms lurked in the mathematical shadows of Einstein's equations for decades, treated more like interesting curiosities than actual objects that might exist in the real universe. Cosmic monsters that lived primarily in the imaginations of theoretical physicists who spent their time solving equations that seemed too strange to describe anything real. It wasn't until the 1960s that astronomers began to suspect that these mathematical abstractions might actually be hiding in plain sight throughout the galaxy, masquerading as ordinary empty space while secretly warping the cosmic neighborhood around them. The first hints of black hole existence came not from seeing the objects themselves, which by definition cannot be seen, but from observing the dramatic effects they have on nearby matter that hasn't yet crossed the point of no return. When material falls toward a black hole, it forms what astronomers call an accretion disk, a swirling spiral of gas and dust that heats up to millions of degrees as gravitational forces compress and accelerate it to significant fractions of the speed of light. This superheated material glows brighter than entire star clusters, creating some of the most luminous objects in the universe from matter that's about to disappear forever into gravitational exile, like cosmic fireworks, celebrating their own impending doom. These accretion disks can shine with the light of billions of suns, making black holes paradoxically among the most visible objects in the universe, despite being fundamentally invisible themselves. The intense heating occurs because gravitational potential energy gets converted to kinetic energy as matter falls inward, and then friction between particles in the swirling disk converts that kinetic energy into thermal energy and radiation. It's cosmic inefficiency in the most spectacular way possible, where the universe turns the simple act of falling into a brilliant light show that can be seen across billions of light years, assuming anyone is out there with telescopes capable of appreciating the irony. The Event Horizon Telescope represents one of humanity's most ambitious attempts to peer directly at the shadows cast by these invisible giants. Using a planet-sized array of radio telescopes coordinated with atomic clock precision to create images of the regions immediately surrounding supermassive black holes. This remarkable engineering achievement has captured the first actual photographs of black hole shadows, revealing the silhouettes of these gravitational monsters against the glowing backdrop of superheated matter spiraling toward oblivion. The images show exactly what Einstein's equations predicted: a dark, circular shadow surrounded by a ring of brilliant light, like cosmic donuts made of warped space-time and electromagnetic radiation. These photographs represent more than just pretty pictures for astronomy textbooks. They're direct confirmations of general relativity's most extreme predictions, proving that the universe really does contain regions where space-time curves so severely that it creates permanent holes in the observable cosmos. The shadows appear exactly the size and shape that relativity predicts, with light bent around the black hole's gravity, creating a phenomenon called gravitational lensing that makes the accretion disk appear as a bright ring surrounding the dark silhouette. It's like having the universe pose for a portrait that simultaneously proves and demonstrates some of the strangest aspects of Einstein's geometric description of gravity. Gravitational wave astronomy has opened another window into the black hole universe, allowing us to detect the ripples in space-time itself, created when two black holes spiral into each other and merge in cosmic collisions that release more energy in gravitational waves than all the stars in the observable universe emit in light. These space-time tsunamis travel across billions of light-years to reach detectors on Earth, carrying information about the most violent events in cosmic history, encoded in distortions of space and time so subtle that they require laser interferometry precise enough to measure changes in distance smaller than 1,000th the width of a proton. The detection of gravitational waves from merging black holes has confirmed Einstein's predictions in the most dramatic possible way, proving that massive accelerating objects really do create ripples in the fabric of space-time that propagate outward at the speed of light like cosmic earthquakes. Each detection tells a story of two black holes that orbited each other for millions or billions of years, before finally spiraling together in a final cosmic embrace that lasted mere seconds, but released energy equivalent to several solar masses converted entirely into gravitational radiation, according to Einstein's famous equation relating mass and energy. X-ray astronomy has revealed entire populations of stellar mass black holes throughout our galaxy, identified by their characteristic signatures when they strip material from nearby companion stars in binary systems. These cosmic vampires create distinctive X-ray emissions as stolen stellar material heats up in their accretion disks, producing radiation patterns that serve as gravitational fingerprints, identifying their presence even when the black holes themselves remain invisible. The X-ray emissions flicker and vary in ways that reveal details about the black hole's mass, spin, and feeding behavior, like cosmic EKGs monitoring the gravitational health of these exotic objects. Modern surveys have catalogued thousands of supermassive black holes at the centers of distant galaxies, each one revealed by the energetic processes occurring in their immediate vicinity as they consume surrounding matter and regulate star formation across their entire galactic domains. These observations have transformed black holes from theoretical curiosities into essential components of cosmic structure formation, revealing them as active participants in galactic evolution rather than passive gravitational sinks that simply accumulate matter without influencing their surroundings. Supermassive black holes aren't just cosmic curiosities lurking in the dark corners of space like gravitational hermits. They're essential architects of the universe we see today, cosmic urban planners operating on galactic scales with the authority to regulate star formation, control gas flow, and determine the ultimate fate of entire stellar communities spanning hundreds of thousands of light-years. Nearly every large galaxy harbors a supermassive black hole at its center, and these monsters play crucial roles in galactic evolution that extend far beyond their immediate gravitational neighborhoods, influencing cosmic structure formation through processes that operate across distances that dwarf our entire solar system. They're not just passengers riding along in their galaxies, but active drivers steering galactic development through feedback mechanisms that can either encourage or suppress star formation, depending on their current appetite for surrounding matter. The relationship between supermassive black holes and their host galaxies represents one of astronomy's most surprising discoveries, revealing correlations that suggest these cosmic giants grow together over billions of years in a carefully choreographed dance of mutual influence. The mass of a galaxy's central black hole correlates precisely with the mass of its central stellar bulge, following mathematical relationships so tight that astronomers can predict one from the other with remarkable accuracy. It's as if galaxies and their central black holes have signed cosmic contracts, specifying exactly how much each partner is allowed to grow relative to the other, maintaining proportions that seem almost designed to optimize galactic stability and star formation efficiency. This cosmic symbiosis operates through feedback mechanisms that make supermassive black holes remarkably effective at regulating their own food supply and their galaxy's star formation rate. When a supermassive black hole feeds actively on surrounding matter, it releases tremendous amounts of energy through jets of high-energy particles and intense radiation that can heat and disperse gas clouds across the entire galaxy, effectively turning off star formation by removing the raw material needed to create new stellar populations. Its cosmic population control, implemented through a combination of radiation pressure and particle winds that can clear gas from regions millions of light-years away from the black hole itself. These jets of high-energy particles can extend across distances that dwarf the host galaxy itself, creating enormous bubbles of hot gas that influence the structure of intergalactic space and regulate the flow of matter between galaxies. The jets operate like cosmic leaf blowers powered by gravitational energy, capable of moving vast quantities of gas and preventing it from cooling and condensing into new generations of stars. When astronomers map these jet-inflated bubbles using radio telescopes, they reveal cavities in the intergalactic medium that could contain hundreds of galaxy-sized volumes, demonstrating the remarkable reach of supermassive black hole influence across cosmic space. The energy source for these galaxy-shaping processes comes from matter falling into the black hole's gravitational well, where gravitational potential energy gets converted into kinetic energy and then into electromagnetic radiation and particle acceleration with efficiencies that make nuclear fusion seem wasteful by comparison. A supermassive black hole can convert up to 40% of infalling matter's rest mass into pure energy, compared to nuclear fusion's mere 1% efficiency, making them the most powerful energy sources in the universe when they're actively feeding. It's cosmic power generation that makes stars look like candles in comparison, engines capable of outshining entire galaxies when operating at full capacity. This energy output creates a feedback loop that regulates the black hole's own growth rate, because the more actively it feeds, the more energy it releases, and the more effectively it heats and disperses nearby gas that might otherwise continue falling inward. The system reaches a natural equilibrium, where the black hole's energy output balances the gravitational attraction that draws matter inward, creating sustainable feeding rates that can persist for millions of years without either starving the black hole or completely depleting the surrounding gas supply. Its cosmic homeostasis, operating on galactic scales, automatic regulation systems that maintain stability across astronomical timescales. The jets and outflows from supermassive black holes also enrich the intergalactic medium with heavy elements produced by stellar nucleosynthesis in their host galaxies, distributing carbon, oxygen, silicon, and iron across cosmic distances, and providing the chemical ingredients necessary for rocky planet formation in future generations of stellar systems. These cosmic recycling programs operate on scales that encompass galaxy clusters, spreading the products of stellar evolution across regions containing hundreds or thousands of individual galaxies. The supermassive black holes serve as cosmic distribution centers, collecting processed stellar material from their host galaxies and redistributing it across intergalactic space through their energetic outflows. Recent observations have revealed that supermassive black holes can switch between active and quiescent phases over cosmic time, alternating between periods of vigorous feeding and growth and periods of relative dormancy when their energy output drops dramatically. These cycles of activity and quiescence correlate with the availability of gas in the galactic center and the efficiency of mechanisms that can deliver matter to the black hole's immediate vicinity. When the central regions of a galaxy are rich in gas, the supermassive black hole can feed actively and regulate star formation through its energetic output, but when the gas supply becomes depleted, the black hole enters a quiet phase that allows star formation to resume until the next feeding cycle begins. This cyclic behavior helps explain the diversity of galaxy types observed in the universe today, from actively star-forming spirals to gas-poor ellipticals that have largely ceased creating new stellar populations. The evolutionary history of each galaxy reflects the complex interplay between its central supermassive black hole's feeding cycles and the availability of gas for both black hole accretion and star formation. It's cosmic ecology, operating on the largest possible scales, where predator-prey relationships exist between supermassive black holes and the gas reservoirs that feed both them and their host galaxies' ongoing star formation, creating a dynamic balance that shapes the appearance and evolution of cosmic structure across billions of years of universal history. And so, dear cosmic traveler, we reach the end of our journey to the edge of the impossible, to places where space and time bend beyond recognition, and where the universe keeps its deepest secrets locked away behind event horizons that serve as cosmic safety deposit boxes with no keys and no visiting hours. We've fallen past event horizons like Alice tumbling down gravitational rabbit holes, stretched through spaghettification that would make even the most flexible yoga instructor admit defeat, witnessed the slow evaporation of infinity itself through Hawking radiation, and pondered paradoxes that would make philosophers weep and mathematicians reach for stronger coffee. Black holes remind us that the universe is far stranger and more wonderful than our everyday experience suggests, filled with phenomena that challenge our deepest assumptions about reality and force us to expand our understanding of what it means for something to exist in the first place. Throughout our gentle descent into cosmic impossibility, we've discovered that black holes are not just the universe's ultimate vacuum cleaners or cosmic monsters lurking in the dark corners of space, but essential participants in the grand architecture of reality itself. They regulate star formation across galactic distances, distribute heavy elements throughout intergalactic space, and provide laboratories where our most advanced theories about the nature of space, time, and information come together in complex mathematical dances that we're still learning to choreograph. These gravitational giants serve as cosmic quality control inspectors, ensuring that galaxies don't form stars too quickly or consume their gas reserves too rapidly, maintaining cosmic homeostasis through feedback mechanisms that operate across billions of light years and millions of years of cosmic time. We've seen how black holes challenge our basic intuitions about almost everything, from the nature of time and space to the fundamental conservation laws that govern energy and information throughout the universe. They exist at the intersection of our most successful theories about reality, general relativity, and quantum mechanics, creating regions where these two frameworks engage in their most intimate and confusing interactions. The mathematics that describe black holes reads like poetry written in equations, full of singularities and event horizons, rotating ergospheres and quantum fluctuations that transform the familiar geometry of everyday space into something far more exotic and mysterious. The formation of black holes from the violent deaths of massive stars demonstrates how the universe recycles matter and energy on cosmic scales, transforming stellar giants into gravitational points that can persist long after the stars that created them have been forgotten by cosmic history. These stellar remnants become permanent features of the galactic landscape, invisible anchors that shape the motion of nearby objects, and occasionally reveal themselves through the brilliant light shows created when they consume matter from their cosmic neighborhoods. They're like cosmic fossils that preserve information about stellar evolution and galactic chemical enrichment across billions of years of universal history. Perhaps most remarkably, black holes have taught us that the universe contains regions that are fundamentally unknowable to outside observers, cosmic privacy zones where information can check in but never check out, creating permanent limitations on scientific investigation that transcend any technological constraints. The event horizon represents not just a boundary in space, but a boundary in the very possibility of knowledge, where the scientific method encounters absolute limits imposed by the geometry of space-time itself. It's humbling to realize that no matter how advanced our technology becomes or how sophisticated our theories grow, there will always be aspects of reality that remain forever hidden behind these gravitational curtains. The discovery of Hawking radiation revealed that even the most permanent-seeming objects in the universe eventually fade away, following cosmic recycling programs that operate on timescales so vast that they make geological ages seem like brief moments in an eternal process of creation and dissolution. black holes evaporate through quantum mechanical processes that connect gravity, thermodynamics, and information theory in ways that continue to surprise and challenge theoretical physicists. They're not just endpoints of stellar evolution, but temporary features of cosmic landscape that will eventually return their accumulated mass and energy to the broader universe through patient processes of quantum mechanical evaporation. The gravitational waves produced by merging black holes have opened new windows into cosmic history, allowing us to witness the most violent events in the universe through ripples in space-time itself that carry information across billions of light-years without being absorbed or scattered by intervening matter. These space-time tsunamis provide direct confirmation of Einstein's most exotic predictions while revealing populations of black holes that were previously invisible to conventional astronomy. Each gravitational wave detection tells a story of cosmic violence and beauty, describing binary dances that lasted millions of years before culminating in final embraces that released more energy than all the stars in the observable universe emit in electromagnetic radiation. As we've explored the strange physics of black hole interiors, the mysteries of information paradoxes, and the cosmic roles these objects play in galaxy formation and evolution, we've glimpsed the profound interconnectedness of seemingly disparate areas of physics and astronomy. Black holes serve as cosmic Rosetta Stones that might eventually help us decode the relationship between quantum mechanics and general relativity, potentially leading to unified theories that could transform our understanding of reality itself on both the largest and smallest scales. So as you drift towards sleep tonight, remember that somewhere out there, black holes are quietly reshaping the cosmos with patient persistence that spans cosmic ages, spinning in the darkness between stars while maintaining the large-scale structure of the universe through gravitational influence that extends across millions of light-years. They're cosmic gardeners tending galactic ecosystems, cosmic recyclers processing stellar remains, and cosmic laboratories testing the fundamental limits of physical law. These invisible giants keep the universe's most profound mysteries safe behind their event horizons, eternal guardians of cosmic secrets that may forever remain tantalizingly beyond our reach, reminding us that reality contains depths that exceed even our strangest dreams and most exotic mathematical fantasies.